So this problem says, on a planet whose radius is 1.2 times 10 to the 7 meters, the acceleration due to gravity is 18 meters per second square, almost twice the acceleration due to gravity on Earth. What is the mass of the planet? Okay, so the radius of the planet is 12 times 10 to the 6 meters. I'm writing it like that just so I'll compare this to the radius of the Earth is 6.4 times 10 to the 6 meters. All right, so the radius of this planet is almost twice that of Earth. And what we want to find is the mass of the planet. Okay, so, bless you. So, m times g on the planet, if you put a mass m on the planet, this is the force with which it's attracting that object. And that object, that is given by g, the gravitational constant, times the mass of the planet, times the mass of the object, divided by the radius squared. This is the gravitational force on the object, which is equal to mass times its acceleration. This is given to be 18 meters per second squared. They've given you, this is given. Okay, so let me rearrange all of this. So the mass of the planet was g, acceleration due to gravity on the planet, radius of the planet square, divided by g. Remember, this guy was measured in 1800. And once this guy was measured, you could measure the mass of planets like Earth and all that kind of stuff. Yeah? So that's why that experiment was called weighing the Earth. Anyway, once you have this, you can get all kinds of masses. All right, so here's the mass of the planet. 18 meters per second square. And G is all right. So you want to take care of powers of 10 first. That's 10 to the 12. And plus 11 is 10 to the 23. It should work out in kgs. That's 18 square into 12 square divided by 6.67. All right, so this works out too. Okay, mass of the Earth is 6 times 10 to the 24 kgs. So this planet is about 120 times more massive than the Earth. Okay? Yep. All right, so it's not 700. 38.1. All right, so the planet is 6 times as massive as Earth. Yep. All right, again, see, once G was known, you could get the mass of objects. Yep. All kinds of objects. All right, this problem says the acceleration due to gravity on the surface of a planet is 3 times as large as it is on the surface of Earth. The mass density of the planet is known to be twice that of Earth. What is the radius of this planet in terms of Earth radius? Okay, so the acceleration due to gravity on the planet is 3 times that on Earth. The mass density on the planet is twice that of the density on Earth. And I want you to find what is the radius of the planet in terms of the Earth's radius. Okay, so mg on any object, the acceleration due to gravity on the surface of the object is given by this formula. So the acceleration due to gravity is that. Okay. Now, so let's do this. Gp over Ge. The acceleration due to gravity on the planet divided by the acceleration due to gravity on Earth is G, mass of the planet, divided by radius of the planet square, divided by G, mass of Earth, divided by radius of Earth's square. Yep. All right. The other piece of information they give us is the density. Okay. So the density of any object of a planet, for instance, is mass of the planet divided by its volume, 4 pi by 3 r cubed. The volume of a sphere is r cubed, 4 pi by 3 r cubed. Yep.
I thought the equation is negative 3m over r squared.
I'm sorry?
For the ground equation, is it like negative 3m over r squared?
That's the magnitude of the force. This force on this object is r hat is a vector in that direction. The negative sign just tells you the force is in that direction. So the magnitude of the force, that's the force. The magnitude of the force is Gmm by r squared. Okay. All right, so the density of a planet is the mass divided by its volume. Okay, so what we're going to do is we're going to convert this into density. So here's what we'll do. Gp over Ge, okay, mp divided by 4 pi by 3 r planet cubed times r planet. We threw in an extra 4 pi by 3, but we are going to do that in the denominator as well. Mass of Earth, 4 pi by 3, r Earth cube, r. Okay, that one of that cancels that, so that's an r square, which is that. This cancels that, and so you have mp over r, rp square, me over re square. The same thing. Okay. So, okay, I'm going to copy this. No, I don't need to. Yeah, okay, I'll copy it. All right, so GP over GE is equal to rho P over rho E times RP over RE. All right. What is the radius of the planet in terms of Earth radius? Well, essentially, they're asking us to find this ratio. So RP okay. All right, so the radius of the planet divided by the radius of the Earth is GP over GE. GP over GE is 3. And the density of the planet is 2 times the density of the Earth. So that's 2 times that, so divide times 1/2. So the radius of the planet is 1.5 times the radius of the Earth. Okay. All right. Make sure you guys understand that. That's on the exam. It says, what is the escape speed of a satellite located at Moon's orbit around Earth? Assume the Moon is not nearby. Well, so if an object is that far away, and they want you to find what is the escape velocity from that object. Okay. What is the escape velocity? It is escaping Earth's gravity and not coming back. Okay. So now we'll do the following. So, and this wants to escape away to infinity. Okay, so this is the initial energy, and the final configuration is this guy has gone off to infinity, and there's the final energy. Okay, so the only force acting during this process was, so you gave it an initial velocity, escape velocity, and the only process that was happening when it was flying away was gravity, which is a conservative force, so energy was conserved. Okay. There is the initial distance, which was Earth-Moon distance. And this is R is equal to infinity. You've gone to infinity. All right. 1/2, there's the mass of the object, escape velocity square minus the gravitational potential energy is mm divided by the distance, Earth-Moon distance. And the final energy is, okay, the kinetic energy is 0 and the potential energy is 0, because here is the expression for the potential energy, and when this goes to infinity, that goes to 0. So that is 0. So you can solve for escape velocity from this thing. So the escape velocity works out to 2g mass so the escape velocity is what object you're trying to escape from, its mass, and what distance are you trying to escape from. The further out you are escaping from, the lower your escape velocity. So from the surface of the Earth, the escape velocity is 11 kilometers a second. But if you're already at the moon distance, then escape velocity is much smaller from there. Okay? All right, so now we'll calculate the escape velocity. So if you have escape velocity, you escape from the gravity of the object. Okay, so the escape velocity from Earth is 11 kilometers a second. The speed of the International Space Station is 8 kilometers a second. And so that's why the International Space Station is not escaping. Right? Okay. What are the speeds of all the satellites that are going around the Earth? Less than 11 kilometers a second. Okay? All right. So keep that in mind. So the escape velocity is this. So now we'll put in the numbers. 2 times 6.67, and now I'm not going to put units because it'll get messy. That's the value of G. Mass of Earth is 6 times 10 to the 24 kgs. And somebody look up Earth-Moon distance.
It's 238,000 miles.
Yeah, I want it in meters
Meters?
or kilometers.
It's 384,400 kilometers.
3.84 into 10 to the 8 meters. Okay. All right, so we'll calculate this. So this is the escape velocity from Earth at a if you started off near the moon distance, okay, a 250,000 miles away. Okay, so let's do this. That is 16 and 24. 16. 16 minus 11 is 5. We'll make this 0.6 and 10 to the 6. And so square root of 10 to the 6 is 10 to the 3 meters per second, and that's good. That's a kilometer a second. And the rest of this is 2 times 6.67 times 0.6 divided by 3.84. All right, so 1.44 kilometers. Okay, so that's the escape velocity to escape Earth's gravity if you start off near the moon distance. Okay, I saw just before we came to class, I looked up the orbital velocity of the moon. Okay, what do you think the orbital velocity of the moon is? Can you say anything about that? The moon is not escaping Earth, so it has to be less than 1.44 kilometers a second. It's 1 kilometer a second. Okay? So if you're bound to any object, then your speed is less than the escape velocity from that object. Okay. Did you guys understand that? Okay. All right, so this problem is about, you guys remember what killed the dinosaurs?
Satellite.
Huh?
Satellite.
So, well, one of the theories is a massive asteroid hit the Earth, it put up so much dirt that for 2-3 years sunlight was all blocked off and all that kind of stuff. Yeah. So that's what killed it. Okay, so this is a sort of a calculation like that. Okay, and we'll calculate. So if an asteroid like this hits, how many atom bombs it's equivalent to exploding. Okay, and then all that those explosions will put up debris in the atmosphere and so on. Okay. So an average sized asteroid located 50,000 kilometers from the Earth with a mass 50,000 kilometers is the radius of the Earth is about 5,000 kilometers. So 10 Earth radii. Okay, that's how far it is detected heading directly, and 50,000 kilometers, you just saw the Earth-Moon distance is about 400,000 kilometers. So just, within the Moon's orbit. Okay. Heading directly towards Earth with a speed of 2 kilometers per second. What will its speed be just before it hits our atmosphere? Yeah. So here's the asteroid, and 2 kilometers per second. And what is its speed? Of course, it'll be going faster. And so what is the speed with which it'll hit Earth? Okay, so initial energy equal to final energy. Okay. 1/2 mv initial square minus g r initial equal to 1/2 mv final square minus g r final. Okay, so you see this is common. That means all asteroids, the mass of the asteroid doesn't matter. All asteroids would hit at the same speed. Okay. What we are interested in is V final. So what I'm going to do is multiply this by 2, so that will cancel. That'll be 2, and we'll bring that on that side. So that will be V initial square plus G, and that is mass of Earth, divided by 1 R final minus 1 R initial. Okay. All right, the final distance is smaller than the initial distance. Okay, so there's our initial, and here's our final. Okay, so this number is bigger than that number. That's a positive number. So final velocity will be greater than the initial velocity. Okay. All right, so let's calculate this. Let's calculate just this piece, ME or R final minus R initial. You guys understand where this is going? Okay, so 6.67 times 10 to the minus 11. Mass of the Earth is 6 times 10 to the 24 kgs times R final. This is essentially the radius of the Earth. What will be the speed just before it hits our atmosphere? Our atmosphere is only 100 kilometers, so which is, we'll ignore that. So 6.4 into 10 to the 6 meters, okay, minus 50 into 10 to the 6 meters. All right, let's take care of powers of 10. That's 10 to the 23 minus 6 is 10 to the 17. So this is equal to, oh no, that's 10 to the 13 minus 6, 10 to the 7. All right, so the second piece is equal to that. All right, so what we'll do is we will convert this to 5.45, 54.5 into 10 to the 6 meters square divided by second square. And 10 to the power of 3 meters is a kilometer. So this is equal to V final square equal to V initial square plus 54.5 kilometer square divided by second square. Okay, so this piece I've converted to that. And now we can put that speed in kilometers square. So the initial speed was 2 kilometers square. 2 square plus 54.5 kilometers square divided by second square. So V final is square root of 58 kilometers square. So this asteroid would hit the Earth at roughly the speed of the International Space Station. All right. So here, what will be the kinetic energy of the asteroid in the previous problem just before it hits the Earth? Compare this energy to the output of the largest fission bomb. A fission bomb is an atom bomb. A hydrogen bomb is a fusion bomb. Okay, so this is a fission bomb, and the output is 2100 terajoules. Okay. Let's see, what is the mass? So the mass of the asteroid is 2 times 10 to the 13 kgs. 10 to the 13 kgs is a car, so this is 20 billion cars. That's the mass of that object. 20 billion cars, yeah. Okay. So the kinetic energy is 1/2 mv square, which is 1/2, the mass is, what did we say? 2 times 10 to the 13 kgs. And we just calculated the velocity to be 7.6 meters per second. So this will come out in joules. That is 10 to the 6 plus 13 is 19. So 10 to the 19 joules. This is how much energy humankind uses in a year. So that's the energy of this asteroid. Okay. So how many bombs is that? So energy of the asteroid divided by energy of the bomb is 5.85 into 10 to the 20 joules divided by 21,000 10 to the 12 joules. So that's 10 to the 15. Okay, so about 280,000 bombs of our largest atom bombs. So you explode about 300,000 of those bombs all at once, and you have a disaster on your hand. Okay. Do you guys have a sense for the problems? Do you want me to do any more problems, or are we good now? More problems? What? Okay. All right, so I'll do one more problem. I'll tell you what these problems are about. The sun orbits the Milky Way galaxy once in 260 million years. Okay, so we live in a spiral galaxy, and the sun is about a third of the way from the center, and nothing in the universe is stationary. Everything is going around something else. Okay, so the sun is, okay. So if you're in a gravitational field, either you fall down to the center of gravity, and if you're not falling down, you're orbiting the center of your gravitational center. So the sun is orbiting the center of our Milky Way galaxy, and it takes 260 million years to complete one orbit. Okay? So that's what this problem is about. They just want you to calculate the centripetal acceleration. The centripetal acceleration is v squared by r. They give you the orbital radius, okay, and the speed is, they give you the period, so you can calculate that. That's what that problem is about. So here is Jupiter, here is one of the moons of Jupiter. It goes around Jupiter and it is orbiting, the orbital period is 1.769 days. Okay. If this were the, do you guys know how long does the moon take to go around Earth? I'm sorry? Yeah, 29 days. And this thing is taking 1.8 days. So that tells you the more massive an object, the faster you're going around. Okay, so from its orbital period and orbital radius, you can calculate the mass of this object. Okay, that's using Kepler's third law. Okay, so maybe we might do that. Okay. What this problem is about is the following. So when an object goes around another massive object, here the velocity is small, here the velocity is large. Okay, so this problem is V1. Okay. At the perihelion, here it's the orbital velocity of this comet is 55 kilometers per second. At aphelion, what is its speed there is the question. Okay. And this is the conservation of angular momentum. Angular momentum at this point is equal to that. So m1 v1 r1 equal to m. The mass of the comet is the same. Okay. So v2 equal to r1 by r2 times v1. Okay. R2 is of course that distance, and this is R1. So this is an easy problem. You can calculate the velocity of the comet at that point. Okay. This is about a black hole. Okay. What would be the Schwarzschild radius if in light years, if our Milky Way galaxy, if you took our entire Milky Way galaxy and turned it into a black hole? How large would that black hole be? Okay, which problem do you want to see? This is, all right. I just want to make sure of the formula. All right, so right, so this is called the Schwarzschild radius. Mr. Schwarzschild published his result within a few months after Einstein published his theory of relativity. So if you take an object that big and squeeze it within this radius, then it'll become a black hole. So you can take let's say an object like that is not a black hole, and squeeze all of that within this radius, it'll become a black hole. Yeah. And this radius is given by C is square root of 2gm. M is the mass you're squeezing into this radius, divided by RS. And that's that formula. Okay. So, all right, C square is 2gm by rs. So this is the radius into which you have to squeeze that object. Okay, if you want to turn this mass into a black hole, you have to squeeze it in within this radius. And what we're going to do is we're going to take the entire Milky Way galaxy and turn it into a black hole. Okay. So if our Milky Way galaxy of 100 billion stars, so 100 billion times the mass of our sun is what they're trying to say. Again, so 6.67 times 10 to the minus 11 is g. The mass is 100 billion solar masses. 100 billion solar masses. C, the speed of light is 3 times 10 to the 8 meters per second, and that's squared. Okay, I haven't, and so this will come out in meters.
It's like,
Hmm?
it's
Just now?
it's still running.
Mm-hmm. All right, so let's take care of powers of 10. That's 10 to the 39 minus 11 is 10 to the 28 minus 16 is 10 to the 12. And that's 2 times 6.67, 39, 28, 16. Yeah. Oh, I forgot this 100, so 10 to the 14. And then divided by 9. All right, so what we'll do is, so that's the radius of this, so that's the radius of the black hole, okay, Schwarzschild radius of the black hole. You took our entire galaxy and turned it into a black hole, okay, and that would be the radius. Now that's just a big number. To give it more meaning, here's what we'll do. So here's the Schwarzschild radius. And again, now this is all sort of a silly calculation. If light traveled from the center to the black hole, how long will it take that to get there? Okay, so distance is speed of light times times. Time flows at a different rate. All that space is all curved and all that. So this is just a sort of a silly calculation. 2.96 into 10 to the 14 meters. Divided by 3 into 10 to the power 8 meters per second. So approximately 10 to the 6 seconds. And roughly 300 hours. Light would take 300 hours to get there. Okay. So it'll be bigger than our solar system. How long does it take for light to get from the sun to Earth? 8 minutes. Very good. Okay. All right, guys.